Okay. Let me go back here. Okay, so let's take a look at this parametric equations right here. So we got x is equal to this and y is equal to this. So what is this going to look like? One way you can sketch a parametric curve is simply by making it a t-chart, except it's not really a t-chart anymore because we have 3 columns. There's 3 variables involved. We have t, x, and y. Sometimes t will have a restriction on it, and sometimes t won't. If there's no restriction, you assume that t is all numbers. So we're going to go from -2 to 3. So I'm just going to go ahead and make a chart here, -2, -1, 0, 1, 2, 3. And then we plug these values into x. And so we have 0, -3, -4, -3, 0, and 5. And then when we plug all these values into the equation for y, we're going to get -1, -1/2, 0, 1/2, 1, and 3/2. And then you plot those points. So if I plot 0, -1, -3, -1/2, -4, 0, -3, 1/2, 0, 1, and 1, 2, 3, 4, 5, 3/2. So these represent points along the curve. Now, notice t has a beginning and an end, and it goes in order. So remember how I said that a parametric equation describes the path of a particle along a curve? So this is what I'm talking about there. These points are going to form a curve, and the path that the particle takes, it's going to start at this point at 0, -1, go through these points and all the other points in between, and end here. So it's going to end up going along this curve. Oh, that's horrible. And that's the path the particle takes. Now, what we do with parametric curves is we want to show the direction the particle is going. So you'll often see arrows going along the curve. Sometimes people just put one arrow. Sometimes people put a whole series of arrows, but they show the actual path of the curve, of the particle on the curve. So the particle starting here at this point goes all the way around and comes back at 5 3/2. So that's a parametric equation. So any questions now on what a parametric equation is? That's just kind of your basic introduction to it. Now, the thing that I do want to show you real quick is on the calculator. So here's our graphing calculator. And I don't know if you've ever noticed or wondered this button down here, that x, t, theta, n, like every time we hit it, we get an x. What's all this other stuff on there? Well, I'm going to hit mode. We've always been in function mode, but notice there are 3 other modes for the calculator. We're talking about parametric equations today, so I'm going to go ahead and choose parametric, and notice what happens when I go to y equals now. It all looks different, and it's asking me for the equation for x and y. We can still put in multiple parametric equations, just like before. We could put multiple functions in, but now it's all changed. And if I go ahead and put those equations that we were just dealing with, so x was t squared minus 4, notice what happens when I hit this button. I don't get an x anymore, I get a t. So t squared minus 4, and then this one, what was it? T divided by 2. So we have that. Now, remember also we had a restriction on t, that t went from -2 to 3. So now I'm going to hit the window button, and that's going to have changed a little bit. So notice now we have a t min and max, an x min and max, and a y min, and there's a y max that's scrolled off the screen. So we can see that the values for all of these have changed. So I'm going to go ahead and say the t minimum is -2 and the maximum is 3. And make graph really fast. Let me see. Ideally, when you hit graph, you're going to be able to see it sketch the curve, and it's going to sketch it in the order that the particle travels. Let's see how fast this goes, though. So that went really fast, but hopefully you saw that. I'm going to go ahead and change my window real quick. Let's go from -5 to 5. So it went really fast, but then you can see it. Now, one other quick thing, I'm going to go back here. So I'm going to highlight this thing that's in front of x. You might have played with that before with functions. We have this like 0 with a dash in it. That's going to actually, now we're going to be able to see the particle along the curve. So it went really fast again. We can actually slow it down a little bit. I'm going to go ahead and just change my t-step. Oops. Well, didn't change it too much. I didn't want to make it too slow, but you can play around with your calculator. And since I'm using my tablet, the processor just makes it run really fast. But that's kind of an use for that. So your calculator actually can play around with stuff like that. One last thing, if we go to the table, you can see the table now has the 3 columns for t, x, and y. So your calculator handles all of this, which is kind of nice. All right, so any questions so far? Okay, so then now to start getting into the calculus of parametric equations, if we want to find dy dx, so it still is an equation on an xy axis. We can still talk about rate of change and slope and all of that. So here's the same exact curve that we were dealing with before. So I'm just going to show you 2 quick methods for doing this. One is eliminate the parameter. And so what that means, remember, t is the parameter. So rewrite this so there's no t. It's only in terms of x and y. And the basic idea here is you want to be able to substitute one function, either x or y, into the other function. In this case, it's going to be really easy to solve for y, or solve for t using the y equation. So we know that y is t over 2, so that means 2y is t. And then if we use the equation for x, but substitute that one in, we get x is 2y squared minus 4, or we can say that. And then we can go ahead and differentiate. But remember, it's not solved for y, so we have to use implicit differentiation. So derivative of x is 1. Derivative of 4y squared with respect to x is going to be 8y dy dx. And then the derivative of a constant 0. And then just divide by 8y, and we get dy dx is 1 over 8y. So that's one way of doing it. And it was pretty easy in this equation, and it just kind of depends on the equations, which method is going to be the easiest. But that's one way to find dy dx for parametric curves. Another way, though, is you don't have to eliminate the parameter. You can just go ahead and rewrite dy dx. Now, I just went ahead and put the curves over here so as a reference, but it's the same equations we've been using. But remember that dy dx can be written as dy dt over dx dt. So then we can just take the derivative of each one of these equations with respect to t. So dy dt, this guy over here, that's going to be 1/2. And dx dt, the derivative of this equation here, is going to be 2t. So dy dx is 1 over 4t. And sometimes it's useful enough to just leave it in that form, but just to show you that we're really getting the same thing, remember that 2y is equal to t. So if we put that in here, dy dx is 1 over 4 times t, which is 2y, and we get the same thing. So 2 ways to do the same thing. So any questions there? Okay. So now to kind of get a real good handle, let's see here, let me get rid of that. To get a really good handle on these parametric curves, let's look at these 3 things first of all. Now, we have this parametric curve, and this parametric curve. One way that you can graph parametric equations is to make that table that we made before. But another way that you can do it is eliminate the parameter. And so if x is equal to t cubed, but we can see that y, which is t to the 6th power, is the same as t cubed squared, we can see that y equals x squared describes this. And you can see that we have the same kind of thing that's going to happen on all of these. Y is equal to t to the fourth on part B, but that's t squared squared. But if x is equal to t squared, then again, this is y equals x squared. And we're going to have the same thing over here. Y is equal to cosine t squared, but if x is equal to cosine t, then we can also say y is equal to x squared. So all three of these equations look like the same thing, but are they really the same curve? So there is something that you have to keep in mind. Sometimes there are just multiple ways of writing the same curve, but let's take a look. So y equals x squared, that's the parabola. We know that's the parabola that goes through these points. I'm going to just quickly sketch it out here. So let's take a look and see what the difference is between these. Let me just get these points. All right. So one way to do it, one way to think about it, let's think about the range of each one of these functions for x and y. So x is t cubed, no matter, and there's no restriction on t on any of these. So we're going to assume that t is all real numbers. So if the domain of t is all real numbers, then the range for x is still going to be all real numbers. So x can be anything, but y, since it's t to the sixth power, an even power, y is going to be a positive value. So, all right, that makes sense actually, because here we can see on this parabola, x is all real numbers, but y is only going to be non-negative. And then as again, we want to still think about the direction of the curve. So t starting from negative infinity is going to start from the negative direction and travel along this curve and go here. So I'm going to go ahead and actually trace this out with a solid line. I'm going to put some arrows in the end to show that this does go forever, but we will put some arrows along the outside of the curve to show the direction that the particle would travel. So that's part A. But now let's take a look at part B. Again, think about the range for t. So no matter what value we put in for t, the range for x, I mean. No matter what value we put in for t, x is t squared, which means x always has to be non-negative. It can be 0 or positive. And y is also 0 or positive. So we're actually not going to have this part of the curve. We're only going to have this part. And then let's also think about, so what direction does the particle actually travel on this curve? Because that's the other part. When you graph a parametric curve, not only do you want to put the path, but you have to put the direction that the particle travels on the path. So starting from negative infinity, starting from t equal negative infinity, when we square it, we're going to have something close to positive infinity. So it's actually going to start with x, over on the positive part. And as t goes from negative infinity closer to 0, the value of t squared goes from positive infinity closer to 0. And then once we get to 0 and go to positive infinity, then we can see the curve is going to go back. So actually what this guy does is it's going to start, from negative infinity, from t equal negative infinity, which means it's going to start from x approaching, or from x being positive infinity. It's going to come down the curve, hit 0, and bounce back. And that's the direction that the particle takes on this curve. So when we change it in terms of x and y, the equations may look the same, but we can see that this curve and the path that the particle takes is actually different from part A. So does that make sense, the difference between part A and part B? Okay. And then for part C, Now let's take a look at what's happening here. So again, t can be all real numbers. So what's going to happen to the value of cosine t? What's the range for cosine t? That's just going to bounce back and forth between positive and -1. So x is going to bounce back and forth between plus or minus 1. But y, because of that squared, is going to bounce back and forth between 0 and 1. So this curve is actually going to be this. But what's going to happen is the particle just goes and swings back and forth between those 2 points. So there's no way to really show that the particle is just bouncing back and forth, except doing something like this. So the point of this was to kind of get an idea, a better feel for what parametric curves are, but also that parametric curves, when you eliminate the parameter, can look the same, but they actually do describe two or three very different paths. I won't just say two, but they can describe very different paths depending on what the actual equations were. Okay, so any questions about that? Okay, so what do we have next? Oh, okay, so then just real quick, just some more basics about parametric equations. If we want to find a parametric equation to represent this curve, y equals 1 minus x squared, there's different ways you can do it. One way you can always do it is like this is solved for y. So let's just let x equal t, and then we'll replace the x with a t for the y equation. So that always works. You can do that. But we could also let x equal t squared, and then we would have this equation for y. So there's different ways to represent a curve that you're given. But just one thing to keep in mind is any restrictions you may have to put based on this kind of idea up here from these three equations. Circles are a big thing that, well, not a big thing, but we often talk about circles with parametric equations. So the equation for representing circles looks like this. And so it's with a radius of r centered at the origin, it's going to be r cosine t, r sine t, or r sine t, r cosine t. These both describe the same circle. Does anybody have a guess if there is a difference between these two, and if there is, what the difference would be? Or maybe there's no difference. Maybe they actually describe the exact same parametric curve. Anybody have an idea? See, if we had more time, this is where I would let you guys investigate it and try to figure it out. But let's go ahead and figure it out together. Make a t-chart. So for the first one, if I let, I'm just going to go ahead, since we're talking sine and cosine, I'm going to go ahead and hit choose 0, pi over 2, pi, and 3 pi over 2. Let's just see what's happening here. So if t is these values and x is r cosine t, then the values go from 1 to 0 to -1 back to 0. And then r sine t is 0, 1, 0, -1. So let's see what this graph looks like. Oh, boy, that's crazy. Anyway, so the first point, 1, 0. The next point, 0, 1, then -1, 0, then 0, -1. And then we know that because of the periodic nature of cosine and sine, it's just going to repeat these points over and over again. So we're going to go back here. So you can see that circle here, and I'm just going to let this equal r. Actually, I guess I should say that these are r's, huh? So, so there's that. Let's see what this looks like here. Again, we're going to go ahead and make a chart. I'm going to use those same values for t because they're awfully handy. But this time x is r sine t, so it's going to go from 0 to r to 0 to -r. And then y is r cosine t, so it's going to be r, 0, -r, 0. So let's plot these points and see what it looks like. So 0r would be up here, assuming that's r. And then we go r0, and then 0, -r, negative r is 0. So, and then we're back up to r. So it looks like, whoops, that is an awful circle. Looks like it's the same exact circle. Did anybody catch, though? There was a difference between them. Does anybody see the big difference between these two circles?
The difference is where they start.
Yes, and
the direction.
Exactly. I just chose to start t at 0, but remember, since there's no restriction on t, then we don't, t isn't necessarily starting here, but the key is the direction. So on the first one, we started off at r0 and then went counterclockwise. So the key is the counterclockwise part. But here on this one, we went clockwise. So that's all the difference is. It's just the direction that you're traveling around the circle. And then does anybody have a guess what would happen to the equations if I wanted to move the origin off or I wanted to move the center off the origin? What would happen now? Like how would I adjust these equations? I know sorry, I'm not giving you a whole lot of think time on these, but so the thing to think about is if we're going to move the center off the origin, we're going to shift the whole circle left or right and up and down. So we're going to take all the x coordinates and either add or subtract a value. And we're going to take all the y coordinates and add or subtract a value. And so it ends up being something like this. If we want to center it at HK, then we just go ahead and take the x coordinate and add h to it. If h is a negative number, that's going to have the effect of subtracting a value, but you just add the value of h to your x coordinates and add the value of k to your y coordinates, and that's going to shift the entire graph, and that moves your origin. So that's true for any parametric curve, not just these circles. So any questions about that? Okay, I think then, yeah, so now we're going to get into the real meat of the calculus part. So we're going to look at arc length, speed, and surface area. And don't worry, this isn't as bad as it may look on the screen right now with all this stuff. So this first screen right here is just trying to derive the equation for arc length. If you remember from functions, this is the equation for arc length. But now let's see if we can go ahead. Oh, that says f of t. That's supposed to be f of x. So, so now we're going to go ahead and try to put this, though, in terms of t using our functions for x and y. So this is just a matter of manipulating it. Remember, f prime is the same thing as dy dx. And one way we looked at dy dx, you can rewrite it as dy dt over dx dt. And then a trick that we can do is multiply by this form of 1. So that's all I'm doing from this line to this line is putting a form of 1 in there. Now, if we take this and split it into two parts, there's the numerator, dx dt. It's under a square root. So I can multiply dx dt squared by this radicand here, and I get this part. So this numerator is right there. But then the denominator, that's 1 over dx dt squared, but under a square root. So the square root and square can cancel out, and I'm just left with this. So I've just taken this form of 1 and now split it into two parts. And then this guy right here is going to distribute to the entire radicand. So dx dt squared times 1 is that. Dx dt squared times this quantity is just dy dt squared. The dx dt squareds cancel out. And then over here, 1 over a fraction is just the reciprocal of it. But now the dx's cancel out, and we finally get dt, which is what we were after, because everything is going to be in terms of t. And this ends up being our equation for arc length. So yes, Siobhan, I'm recording this right now so that you'll be able to see this later. So any questions about that? I should look at the other things. You guys answered that. You're so good. Okay, so then this kind of summarizes it. There's one key thing here. So this is the formal thing now. To find arc length, you use this equation that we just derived up there. But the one thing is right here that the curve can't intersect itself. If it does intersect itself, you have to divide it into different parts. Like, let's just say that the curve, oh, let me change back to a normal pen. The curve did something like that. So it's intersecting itself right here. You're going to look at the values of t that would create that part of the curve and make one integral. And then you would have to look at the values of t that make this part of the curve and make another integral out of it. So that's the only thing that you do here. So I know I went through that kind of fast, but are there any questions how we got this equation? All right, so then I have this equation here, or this problem. I'll scroll up a little bit more. I have it worked out. But a circle with a radius of 1 rolls around the circle of radius 4, creating an epicycloid, as shown in the picture. I don't want to show the picture because I'm going to give stuff away. But I do want to show you what an epicycloid is. Why aren't you showing the screen? Oh, hang on one second. Let me go back. Let me do this. Oh, sorry. Hold on. Let me, it's nothing exciting, but all right, there we go. So here's the idea of an epicycloid is right here. If we were to take a circle, the same radius, and just rotate it around another circle, you follow the path of one point on the circle. So this is an example right here of an epicycloid. Let's say that the circle that's rotating around the other one is half the radius of the big circle, then it ends up creating 2 petals. If it's 1/3 of the radius, so if B is 1/3 of A, now it creates something with 3 petals. Our example looks more like this one because the small circle has a radius of 1, but the big circle has a radius of 4. So it's going to create this picture right here. So that's what we mean by one circle's rotating around another circle, and that's an epicycloid. So, oh, I need to open that again. There's unit 10 right there. Okay, so that's this picture right here. So any questions what an epicycloid actually is? I mean, it's not very exciting, but I wanted you to get an idea of what this was trying to describe. Okay, so then just like when we were dealing with the arc length formula before for functions, it's often easier to find the derivative because remember, so let me bring it down. This is the equation here. So we're going to find the derivative for the function for the x coordinate and a derivative for the function for the y coordinate. And, try to find an expression for this simplified before we actually put it into the integral. And so I would encourage you guys to try this one on your own at home. It's good practice for trigonometry and just kind of algebraic manipulation. But real quick, I'm going to kind of walk through it quickly. If x is this equation, then when you take the derivative, you get this. And when you square it, this is a binomial, so you're going to have to do a binomial squared. So if this is a plus b, then you have a squared plus 2ab plus b squared. And then I just factored out a 25. But unfortunately, nothing else simplifies here. They're all different. That's the argument here is t, and the argument here is 5t. So I cannot combine these. So that's the derivative squared for the x coordinate. Now for the y, it's very similar, except instead of starting with cosine, we're starting with sine. So we take the derivative, we square it, and I factored out a 25 again. But now the last part is to add these two together. And so looking at these two things, there's a nice little trick we can do here. I have a sine squared plus cosine squared, and they have the same argument. It's sine squared t plus cosine squared t. And so we know that that is equal to 1. And then at the ends, we also have sine squared 5t plus cosine squared 5t. So that creates another 1. And then here, well, unfortunately, they won't combine yet. There is a -2 on both of them, though. So I factored out the -2, and I was left with this. But hopefully now this formula looks familiar. Sine A sine B plus cosine A cosine B. That's our difference formula for cosine. That's cosine A minus B. And then this was 2. These ones combined to a 2. So I factored out a 2 from here. That's why the 25 changed to 50. And we wind up with that. And then because cosine is an even function, we can actually simplify it to this. So any questions where I got that from? All right, so now that's pretty simple. We're going to plug it into our integral and see what this looks like. So remember, all of this goes under a square root in the integrand. So, whoops. So it looks like this. And, but how are we going to integrate this? If only the square root wasn't there, this would be really easy to integrate. But this is where, and unfortunately, this is one thing you guys aren't going to get a lot of practice with. In this unit, it comes up a lot. Power reducing formulas. And so we're going to use it here. We want a way to get rid of the square root. If we could just make the integrand as a quantity squared, we'd be able to get rid of it. And one way you can do that is power reducing formulas that look like this. It's actually derived from the cosine double angle formula. So, if you multiplied both sides by 2, and then put the 1 over here, you could have cosine 2a is equal to 1 minus 2 sine squared a. It's that double angle formula just rewritten. But since we have that, now remember the argument over here is 2a and the argument here is a. So if this is 4t, we're going to take half of it and make it 2t here. But to go from here to here, I just used the power reducing formulas. But now I got it in terms of something squared, and 5 times 2 is 100. Well, conveniently, the square root of that is 10. The square root of sine squared is just sine, and now it's much easier to integrate. And then when you integrate and plug in your values, you get 40. So any questions about that? Now, there's one thing I just kind of glossed over, and that is the limits of integration. So this is something that it might take a little playing around with the values, but I'm going to go back up here. We kind of saw it from before when we made the tables for the circles, when we made these tables here. But in order to create just one petal of this epicycloid, and you can plug in values and see that it's going to do it. If we go from 0 to pi over 2, now be careful. Don't just assume, like if we think of a unit circle, this is 0, this is pi over 2. Don't automatically assume that that's going from 0 to pi over 2. You do have to think about the actual values it creates and the path that it traces. But 0 to pi over 2 is going to create one petal. And so that's why I went from 0 to pi over 2, but that's only one petal. So I had to multiply by 4 to get all 4 petals. So that's arc length in a nutshell. Any questions about that? And don't worry, we're pretty much done now, which is nice. So the other thing I wanted to talk about was speed. But remember, speed is ds dt. Actually, I should say, where s is the distance, but it's like arc length then. And so this is like the derivative of the arc length. So if we're going to take the derivative of the arc length formula, it's the derivative of the integral. And so thinking about fundamental theorem of calculus, that's why the integral just seems to disappear, because it is. I mean, the derivative of the integral, they cancel out, and you're just left with the integrand. So if you ever want to find the speed of a particle on a parametric curve, then you just work this out. So that's speed. I don't have an example for that. I don't have any more examples worked out. They're all pretty much now, once you know the formula, you just plug into the formula. It's not really a trick to it. So then the last thing is surface area. And this surface area formula is very much related to our surface area formula for functions. So rather than deriving it all again, if you compare it to our old surface area formula, it was 2 pi r and then the arc length. And this time r, it's going to be, it depends on which axis you're rotating it around. If you're rotating around the x-axis, then this in the picture represents r, and this is going to be based on the y-coordinate. And so that's why this is g of t. But if you're rotating about the y-axis, now this represents r, which is going to be based on the x-coordinate, and that's why r is f of t. But other than that, it's just like our surface area formulas from before. And that's your brief introduction to parametric equations. So I know that was a lot to take in. But do you have any questions right now over parametric? I know. So the big takeaways from this, honestly, it's not as bad as it seems. The big takeaways are that a parametric equation describes the path of a particle on a curve. And that's really important. It's not just the curve. It's the path of the particle on the curve. And that's important when you think about, like this kind of idea. We may have these parametric equations which seem to represent the same curve, but it's the path of the particle on the curve. The path is different on all three. So definitely want to really emphasize that part about parametric equations. It's not just the curve, it's the path of the particle on the curve. So that's one big takeaway. And then really the other things to keep in mind are just the formulas. So we have this formula for arc length. It can get a little messy to deal with, but it's just a formula. It's a straightforward formula. Take the derivative of the x-coordinate, the derivative of the y-coordinate, square them, add them, take the square. Here's a formula. We have the formula for speed. Again, a straightforward formula. It may not always be the easiest to work with, but understanding the formula is pretty easy. And then surface area. So it's not as bad as it seemed. I know that was a lot of information, though, to throw at you. So any questions on that? Okay. I'm so glad that you guys all showed up. Hold on one quick sec. Before you sign off, let me do one quick thing. Okay, I had to take attendance real quick. So like I said, there's not going to be any homework. A lot of you guys are seniors. I want to take it easy on you. If you want to do, I'll tell you what, I'll post what I would have given for homework. And if you were just dying to do some stuff, you can go ahead and do the homework, and I'll post my solutions too, so you can see it, but I'm not going to grade anything. You guys, your grade is fixed. So, but with that said, I'll stick around if you have questions. Otherwise, thank you all for showing up, and I'm glad the guilt trip worked, so that most of you are here. But if you want to go now, you're free to go, and I'll stick around if there's questions. Thanks, guys. Nope, no final, Shivam. You're welcome. See you guys later. Bye. Miss you too. You're welcome. See you all later. Yay. I'm glad you learned something new. It's always nice.